We will now be moving on to our second talk. I am delighted to introduce Professor Dr. MarcoHutter, who runs the Robotics Systems Lab at ETH Zurich. The title of his talk is Learning to Walk. So he will introduce us to robots that are highly mobile and can move through different environments. So MarcoHutter is assistant professor for robotics system at the ETH Zurich and the founder of the Anybotics research company. His research interests are in the development of novel machines and their intelligence to work in unstructured environments. And he has created some of the most advanced legged robots and mobile manipulation systems that find applications various real-world scenarios. He is a member of the National Center of Competence in Research on Robotics and on Digital Fabrication, and his work has received many awards, most recently an ERC Starting Grant. So we will now hear Dr. Hutter speak in a video that has been pre-recorded, and afterwards he will be here for us to discuss his work in a Q&R.
Thank you very much for this kind introduction, and welcome also from my side to this first session on assisting the human. And I would like to show you in how we can do this using autonomous legged robots. Imagine a situation like this: environmental disasters, whether it's a nuclear disaster, earthquake, or forest fires. What happens today is that we have to send humans at the forefront to fight them. But not only there, we're sending people on a daily basis, 1,000 meters underground to mines. We're sending them offshore, kilometers off the coast, or they have to do unpleasant work in sewers or unhealthy and dangerous works on construction sites. And not only here, also the latest corona crisis has unveiled that we do not have sufficient robotic technologies that can really work in all these challenging conditions. And this is what drives my research. I have been investigating the development of systems that can work in these environments for the last decade. In particular, I was focusing on the development of legged system, which started as simple research systems that went over to demonstrators that we could use for first field deployment. And in 2016, we created our spin-off company, Robotics, which now commercializes quadrupedal systems, in particular for industrial inspection. We are today more than 60 people headquartered in Zurich. And I would like to take this opportunity here to give a little bit of a deep dive in how we're applying robotic systems today for industrial inspection or to help the human. Now, why industrials? If you do an analysis of the different sectors, you see that the industrial sector is by far the one that has the least level of digitization. It's a capital and labor-intense industry, where the digitization of physical assets and when providing automation tools has a huge potential. Now, what we're doing is we are providing a system to the plant operators, which gives them all the information necessary in order to maximize the equipment uptime and to improve the safety while reducing costs during these operations. When we talk about industrial inspection, it's not only one industry, it's actually like many different industries, which from an environment perspective look very different. But once you have solved the locomotion problem and you have systems that can go around smoothly in all these different domains, the inspection part is actually very similar in all these different areas. What we are providing is what we call an end-to-end solution for inspection. First, we have a system that has a huge level of mobility in pretty much arbitrary environments. Second, we equip that robot with superhuman inspection intelligence. And then third, we provide the operators with very simple means for automated workflow, from deploying the system, showing it how it works, to like gathering and collecting data on the industrial side. So let me start here with mobility, which is really one of the core aspects of our technology and also part of my research. Legged systems have the ability to, in principle, overcome pretty much arbitrary terrain, just like humans or animals. They can walk stairs, get across steps, gaps, they can do slopes. And very importantly for industrial environments, they can also move omnidirectionally, so sidewards, turn on spot, and by that navigate also in cluttered and very tight spaces. And we can do this with a locomotion speed, which is about the human walking speed when we would do an inspection task. Moreover, besides just moving around, legs also allow you to become a lot more versatile. So assume a situation where the robot has fallen, we can use legs in order to get up and continue to operate. Now, to achieve this level of mobility, one of the key elements that we have been doing fundamental research was use of machine learning, and in particular reinforcement learning, for training locomotion policies. To this end, we're generating simulation environments where we can train agents over days and months, collecting a massive amount of data that allows us to generate locomotion control policies that we can then take and deploy on the actual system. Now, interestingly, with these methods, you can not only make systems walk reliably, you can also make system a lot more versatile. You can achieve behaviors like this. So you see here how the robot realizes that falls over, does a flip, stands up again, and continues to operate. In fact, you can put the robot to an arbitrary configuration on the ground and will find a way and get up and continue to operate. These are levels of mobility that using classical control methods were not possible to achieve. And now with like this new way of using machine learning with simulation and good understanding of the robotic hardware, really allows us to generate the next level mobility. And it shows a little bit in where this goes, like really robots that have a level of agility and mobility similar to humans or animals. We're also not interested in just having that deployed in lab environments, but much more try to make solutions that can go over arbitrary terrains. To this end, we apply so-called curriculum learning, so that better the robot becomes in simulation, the harder we make the environment, until we have a system that is really able to get across all kinds of different terrains. And you're randomizing the type of terrains such that the reality, which you haven't seen before, is kind of a subset somehow of that. And we achieved robust zero-shot generalization. So first time we deployed on reality, an unseen terrain, the system will just smoothly walk across that. And this is the basis that allows us to deploy the system in some of the most challenging environments, whether it's like outside rubble field, underground, muddy terrain, slippery environments, steep inclination, stairs or step, and the robot will just smoothly get across that. And this is the basis for many applications that can fall on top of that. Assume you have robots now that can just go to an arbitrary place and you can put an application on top of that. Now, obviously, these machines have to be very robust because they have to work under some of the harshest conditions. So our machine is IP67, which means it can still work while it's diving underwater for a meter. It's very rugged. It has active lighting also that it can work independent of the environmental conditions. So even if it's dark, you don't have to like put artificial lights or change the environment for the robot such that it can work. It can just work in arbitrary conditions. It is tuned to be fully autonomous in large-scale settings. That means the robot has to carry perception sensors with it, like this LiDAR sensor on top, in order to localize. It then also detects obstacles and the terrain in front and around the robot and decides what it can get across or where it has to move around. So there's like 6 time-of-flight sensors, 6 stereo cameras around the robot, and the LiDAR sensor that allows to get a very detailed understanding of our environment. For installation, there is 2 ways in operating the robot. First one is so-called show and go. What we're doing here is that we have an operator first guiding the robot around an unknown site. By doing so, the robot maps the environment and then uses this map in order to localize later for the inspection tour. And if there's a change in the environment, it can then locally adapt its navigation routine in order to still fulfill the inspection path while not colliding with the environment. The second way, and this is becoming a lot more common meanwhile, is that you're starting from a CAD model or a digital twin of the environment and use this in order to tell the robot what to do, and then also in order to localize while you're on site. So you have the onboard sensors that collect data, and you localize with this data with respect to your digital twin of your environment. Then you want to have machines that have full autonomy, which means that they have to go back, recharge in order to continue to operate. And that's particularly useful if you want to deploy several of them at remote locations without human observers nearby. The system is equipped with a variety of payloads. So here, one example is a pan tilt head equipped with a RGB zoom camera, thermal camera, and acoustic sensors that allows the robot to accurately perceive the environment. Now, depending on the application, you can also swap that, put the different payload on top. We are using this payload in order to do inspection, and all the inspection, not only the data collection, but also the data interpretation happens on the robot itself. There's different types of inspection, for example, visual inspection, thermal inspection, or acoustic inspection. Visual inspection works the following way. You have an understanding from your digital model of the site or from your teaching period in where your object of interest is. The robot finds that, searches for this in the image, zooms in, and reads out the values. It directly does the interpretation while doing this inspection task and provides this back to the operators or to an ERP system or whatever. Then we can do health checking. So while moving around, measure the temperature of all devices. And if you detect a change in temperature from one day to another, you may realize that there's a bearing that could have an issue or a motor that might break in the near future. You can also detect events which are supposed not to happen. For example, here a gas leak that gives you a spike in spectrum when you do your analysis of the acoustic sensors. And lastly, we do 3D environment scanning, which allows us to do precise detection of changes in the structure. I want to finish my talk with a couple of examples in how we're deploying these Leggett robots in reality. You see on the left-hand side, BASF in Ludwigshafen, where we have two robots installed, one equipped with an acoustic sensor, another one with a pan tilt head within visual inspection sensors. These robots are localizing with respect to the digital twin. We can then use this CAD model also to tell the robot what type of inspection tour it has to take, where the points of interest are for doing inspection. This can be done multiple floors, and the robot then robustly executes this over longer mission times. On the right-hand side, you see a deployment on an offshore site, which is particularly interesting in the oil and gas domain. Very similar inspection task. You first give the routine and the robot moves around. In these types of environment, often there is no digital model of available. Things have changed a lot. So we're typically teaching the robot in how to navigate around and then have it executing this predefined routine. And on the left-hand side here, you can see a rolling stock inspection. So both inside and outside the train to see if everything is correct. Again, like visual inspection, thermal inspection. And then on the right-hand side, this is a construction site reality capturing and monitoring, both for the progress monitoring of the build status. And at the same time, you can also use this in order to identify safety hazards and then like call a human to relieve them. With this, I'm at the end of my presentation. I thank you very much for your attention, and I'm opening up for the discussion. Thank you.
Thank you very much, Professor Hutter. This was a really fascinating talk, and I'm very much looking forward to discussing with you now. So maybe I can start with a first question. So your developments allow for new uses for robots across a number of work sites. What would you say are the key benefits of these applications for society? What do you see as a kind of the key contributions these robots can make to our societies of tomorrow?
So I think the biggest gain, and that's also what you mentioned here, is that we can bring robots from the factories, from inside, like controlled and structured environment, to the outside world. And by that also take over some of the really dirty and dangerous jobs. I've shown this on the second slide a little bit. Today we have like plenty of working places in mines, in sewers, offshore, which is really dangerous for humans, and where I think we should not send humans anymore to do the jobs. And for these types of environments, that's where I see like machines as I presented today to be very useful for our society.
That's very interesting. Maybe we can expand on this a little bit. So there's often worries that, the robots will come and take our jobs, right? So I have a sense that the relationship that you're sketching there is a different relationship between human workers and robots. Could you elaborate on that a little bit? How do you see that relationship between human work, robots, and do we have to worry that the robots are going to replace human workforces?
So personally, I don't think that we have to worry. Of course, there is a transfer in how the working places, the individual tasks that humans are doing, how they look like. But I see much more that there's a huge need for robots. So to give you some examples, I have people approaching me on a yearly basis saying, I have, for example, a plastering company. They don't find people anymore. They want to have robots that do the jobs because simply otherwise they cannot fulfill anymore the customer's needs. I think we have a lot more like these things where people don't want to do the jobs anymore and we want to have robots that can take over and help us out there. Same happens as in construction, agriculture. We have a lot of jobs which are just new coming up. You're going to see this also later in the session of Alin, where we're talking about space mining, space exploration, all of that. But it's just places where we should not send humans, and robot provide us these opportunities to still go there and do some exciting jobs.
That's very interesting. Thank you. And where would you say are maybe the key technical challenges for reaching these goals that you've just sketched?
I think we're still struggling in having the right level of autonomy in these systems. So robots are still stupid compared to a human. We have to tell them exactly what to do. They cannot properly assess many of the situations. If things change a lot, it's very hard for them to take the right decisions and right actions. I think that's a place where we still have to improve a lot in understanding the environment and having more meaningful, let's say, use by the robot itself.
Mm-hmm. Thank you very much. I'm just checking if we have any questions from the chat at this point. If not, I will ask you one more question. So I was wondering, in your work, are there any questions, social questions, ethical questions that are coming up in your work where you feel like, oh, that would be interesting to address in more detail, or you would be interested in interdisciplinary collaboration around these topics?
Absolutely. I think robotics in general has to have a very strong dialogue with all kinds of different disciplines in how we deploy these machines in the future, how they will interact with our society, what do they help us in the future, and where do we see problems. And we have to do this early enough. We cannot just have a technology there and then all of a sudden like everybody has to transform instantaneously. I think the lucky situation that we have in robotics is that robotics is not an extremely transformative technology. It takes a lot of time until this is really embedded in our ecosystem, in our industry. And from that perspective, we have also time as a society in order to adapt to these changes.
Thank you very much. Thank you very much for your very interesting talk and for this discussion.